Welcome back. This is video lesson number 7. Today we're going to be talking about integration by parts. Integration by parts is a method for evaluating indefinite integrals. It's very similar to substitution in the way that you pick apart the integrand of an integral and make changes to hopefully obtain an integral that is simpler that you can evaluate. Let's get started. So remember that the substitution method came from looking at the chain rule and seeing what it said about integrals. For integration by parts, we're going to do the same thing, but with the product rule. So here's the product rule. I have two functions, which I'm calling u and v, and the derivative of their product is this sum, where I form two terms by taking the derivative of one of the factors and leaving the other the same. So I have v times the derivative of u plus u times the derivative of v. So now let's turn this into a statement about integrals. If I take indefinite integrals of both sides, on the left-hand side I'm just left with u times v, and on the right I get the indefinite integral of each of those terms, which I'll write like this. Here's that same expression again. I'm going to manipulate this a bit. I'm going to take this v times du over dx integral term and subtract it over to the other side and switch the sides of the equation to get this. And then notice I've changed the parentheses a bit. Remember that dv dx is the derivative of v with respect to x, and if you think of this as v prime of x times dx, then we can call this dv, kind of like we did in the substitution method. Similarly, we can call this du, and so I get this formula. The integral of u dv is equal to u times v minus the integral of v du. And this is called the integration by parts formula. Okay, so remember this. I'll write it down on the next slide. We're going to do an example that shows how we actually use this. So here's an integral that so far in this course we don't know how to handle. But the first thing we're going to do is we're going to break the integrand, so the integrand is x times cosine x, into parts u and dv. Next, from u, we can differentiate to get du, and from dv, we can anti-differentiate or integrate to get v. And then we'll plug everything into the formula, which, remember, the integral of u dv is u times v minus the integral of v du. So once we have v by integrating dv and du by differentiating u, we can put everything into the left-hand side, and you'll see we'll get a simpler integral. So for this one, x is going to be u, and cosine x dx is dv. The part that you call dv always has the dx inside it. So I'll write that down again. I get u is x, and dv is cosine x dx. So I differentiate the u to get du, and remember, when I differentiate x, I get 1, but we're also going to write the dx in here. So we're keeping things when we can as a relation between differentials. And over here, I take an antiderivative, so I get v is sine x. Okay. So now the integral of u dv, which is x cosine x dx, following the formula, I have u times v, so that's x times sine x, minus the integral of v times du. So v is sine x, and du was just dx, because x was equal to 1. And now look, I have an integral here that is simpler than what I started with, so I can actually do this without any more tricks. So my final answer is x sine x, and an antiderivative of sine is negative cosine, so I have plus cosine x, and a plus c at the end because it was an indefinite integral. Okay, so that's how we use integration by parts. You can always just follow these steps. The hard part, or the tricky part, is figuring out how to break up the integrand into u and dv. Eventually you develop an intuition for which types of factors in the integrand should be the part that you differentiate and which should be the parts that you integrate. But for a while, you might just have to try things and see how it works out. So the rest of this video is going to be exercises illustrating various ways in which we use integration by parts to do integrals that we previously could not have done. So here's the first one. I think you should pause the video now, see if you can solve it using the technique from the previous slide, and then unpause and watch the solution. Okay, so first I'm going to do this one the wrong way. Let's say that I said I want to differentiate the e to the x and anti-differentiate x times dx. You'll see why this is the incorrect choice. When I differentiate u, I get du equals e to the x dx. And when I anti-differentiate the v part, I get v equals 1/2 x squared. Oh, no dx, sorry. Just get 1/2 x squared. And now if you remember the integration by parts formula, what I'll end up with is u times v, which is going to be e to the x times 1/2 x squared, minus the integral of v times du, so 1/2 x squared times e to the x dx. So notice that this new integral that I have to do is actually worse, right? This power of x increased. Okay, so this is kind of what I was talking about. Eventually you develop intuition for which parts should be the u and which parts should be the dv. Whenever you have x to some power, like a polynomial term like x or x squared, you want that to be the part that you differentiate, because differentiation will lower the power to make things simpler. So let's put a big red X through this. This is not the way we want to do it. Instead, what we're going to do is the opposite. So we're going to say let u be x, like we did in the previous problem, and dv will be e to the x dx. So I differentiate u, I get du equals dx, and I anti-differentiate v to get e to the x. Right? Remember, antiderivative of e to the x is just e to the x. And so I get the integral of x e to the x dx, the integral of u dv is u times v, so x times e to the x, minus the integral of v du, so e to the x dx. And now again, this is an integral that I can actually do. It's just e to the x plus c, so my answer is x e to the x minus e to the x plus c. There we go. On to the next one. Here's another exercise. Give it a shot, and then we'll go over it. Okay, so just like in the previous problem, I want to differentiate the part with x and anti-differentiate the other part. So we'll say u is x squared, and dv is cosine x dx. So I differentiate u, I get 2x dx, and I anti-differentiate v, and to get a sine x, just as the antiderivative of cosine. So we put that into the integration by parts formula. I have u times v, which is x squared sine x, minus the integral of v du. So I'm going to have 2x times sine x times dx. Okay, now I notice that this integral is simpler. It's a x instead of an x squared, but it's not quite simple enough that I could just do it off the top of my head. So actually what we're going to do is another integration by parts. And I'll use a different color, but I'm still going to call these things u and v. So this is going to be, again, that's going to be u, and this is going to be dv. So u is 2x, dv is sine x dx, and then I differentiate, get du is 2 dx, and anti-differentiate to get v is minus cosine x. And now we're ready to write down the integration by parts formula again. I have x squared sine x from before, and then minus, there's going to be a bunch of minus signs here, so I'm going to put parentheses. U times v is 2x cosine x minus the integral of v du. So v is minus cosine x. Du is 2 times dx. So this is just now a antiderivative of 2 times, well, it's twice the antiderivative of cosine x, which I know how to do just off the top of my head, so I can write down the final answer. I have x squared sine x. There's a, oh, I dropped a minus sign, didn't I? Yeah, this should be u times v, which is, remember, minus cosine x. So this should be plus 2x cosine x. And then we have 1, 2, 3 minus signs in front of the next term, so we're going to have a minus 2 times the antiderivative of cosine, which is sine, plus c. So there we go. So that's an example where we have to use integration by parts twice. And you can see that it's precisely because we have an x squared in the integrand that we had to do it twice. You can imagine if this was x to the 5th times cosine x, you could do integration by parts 5 times, which would be a bit of a pain, but you could definitely do it. Next exercise, this is a definite integral. So make sure you're careful about evaluating, right, when you do the integration by parts. So I'll write down before you do the problem. If I'm doing a definite integral by parts, so if I have u dv here, I still have uv minus the integral, and the integral keeps the limits of v du. The only thing is I need to evaluate this limit from a to b. Or sorry, I have to evaluate this term from a to b. Otherwise, it's still a function of x, and I'm supposed to get just a number for a definite integral. So make sure you evaluate this part after you do the integration by parts. Okay, go ahead, give the problem a shot, and then we'll go over it. So the way we break this up into parts is sort of non-obvious if it's the first time you're doing it. What we're going to do is we're going to call this part u, the differentiable part, and then dv is just dx. So if you were just looking at the integrand as ln x, you might not have seen how to break this up into two pieces, but the dx, and you can think of you're writing a natural log of x as ln x times 1, and then the 1 is the extra factor that you're calling dv. So anyways, we have u is ln x, and dv is dx. So I differentiate u to get du is 1 over x dx, and then the integral of dv is just v, and the integral of dx is x, right? So putting that into the integration by parts formula, and remember, don't forget about the limits, I'm going to have u times v, which is x times the natural log of x, evaluated from 1 to 3. And then I have minus the integral, still from 1 to 3, of v times du. So I have x times 1 over x dx, which is just dx. Okay. Now I can evaluate this between the limits. So I have 3 natural log of 3 minus 1 times the natural log, let me write that better, times the natural log of 1, minus the integral from 1 to 3 of just 1 is x evaluated from 1 to 3, so that's just going to be 3 minus 1. And so I get 3 times the natural log of 3. The natural log of 1 is 0, so this term vanishes, and then I have minus 2. There we go. And I'll just add in a different color here something that came up along the way. We've actually found the indefinite integral of the natural log function, which is worth taking note of because it wasn't something we have gone over before. It's x ln x minus the indefinite integral of just dx is x, and then I have plus c. Okay, so that's something you can memorize this if you want, or just remember that you do it by a quick integration by parts. Okay, this is the last exercise. It's a bit tricky, but give it a shot, and then we'll go over it. Okay, so I'm going to set u to be e to the x, and then dv is sine x. It doesn't actually matter how you do this one as long as you're consistent, and I'll show you what I mean by that in a second. So I have u is e to the x, and then du is e to the x dx, and dv is sine x dx, and so v is minus cosine x. So what do I get? I get u times v, so that's minus e to the x cosine x, minus the integral of v du, so that's going to be plus the integral of e to the x cosine x dx. Well, that's weird. I started with something e to the x times trig function dx, and I simplified it back to that. So this is another one of those silly, classical, tricky integration by parts problems. The thing I have to do here is integration by parts again. Right? You can imagine I started with e to the x sine x, and I did integration by parts, and the sine changed to a cosine. If I do it again, I'll get e to the x times cosine x as the integral that's left over, and then I'll be able to solve for this integral. So let's do it again in green. So this is going to be u again, this is going to be dv. As long as you make the same choices here as you did the first time, it works out. So u is e to the x, dv is cosine x dx. So I get du is e to the x dx, v is sine x, and then so I have the negative e to the x cosine x left over, and then I'm adding u times v, so e to the x sine x, minus the integral of v du, so I have e to the x sine x dx. So actually I'm going to introduce a third color, which let's go with white so I don't have to write in red. The magic here is that I got the integral that I'm trying to solve. So the thing that we do, let's give this a name. Let's call it I. So what I've shown is that the integral I is equal to negative e cosine x, negative e to the x cosine x plus e to the x sine x minus I. So I can solve for I by adding I to this side. So in other words, move this term over here. So I get 2I is equal to this stuff, which just write. It's everything besides the i's in this expression. And so finally I can divide, to solve I just divide by 2. And so writing it out, I get that I is equal to 1/2 of minus e to the x cosine x plus e to the x sine x plus c. Okay, we added the plus c at the end, even though we actually should have, well, okay, we didn't have to have it here, but we should always have it in our final expression. Okay, that was the last problem I have. This kind of thing where you have to give a name to the integral you're trying to find and then solve for it algebraically shows up every once in a while, and it's a good thing to look out for because it's not always obvious that you should do it when you do integration by parts once and you get to something similar but not exactly the same, and then you do it again, you get to something that's exactly the same as what you started with. Okay, that's the end of the lesson. I hope you got something out of that. As always, ask me any questions in class or in office hours, and I'll see you next time.